Hi there! Since the last video on using the Arduino to generate tones of variable frequency, I received several comments, and most of them were very constructive, giving me opportunities for improving the original design. Today my work will be based on specific comments received from Steve Harbin, my interpretation and adaptation of his comments. Many thanks to Steve for the help provided. There were two big issues encountered in the previous experiments. The first one was about the range of audio frequencies that could be obtained. The second was about the glitches in the audio signal clearly visible on the oscilloscope. There are several approaches to fix the first problem, the simple one being moving into a different and faster platform than the Arduino UNO. One possibility suggested by Steve is to reduce the number of samples at the increase of the frequency. He even suggested a program to do that, which is visible in the comments from the last video. I tried that program and it helped in increasing the maximum frequency reachable by the Arduino. However, that solution made me also think about other options I could try. First of all, I could greatly reduce the CPU load by reducing the number of samples per period regardless of the frequency. I originally used a number of samples based on 6-bit because I wanted to be able to reproduce not just sine waves, but also triangular and square waves. But those waves depend heavily on high harmonics, and so to reproduce them nicely I had to use a high number of samples. Not so with the simple sine wave, which has no harmonics at all. Technically, if I wanted to reproduce a single frequency using a sine shape, I would just need 2 samples per second and use a low-pass filter with a cutoff frequency of the same value to regenerate the whole sine wave. But I need to have a large range of frequencies, and so I have to use multiple samples. However, I don't need so many samples as for generating triangular and square signals. So my final decision was to give away the generation of triangular and square waves, which I can still obtain manipulating analogically the sine wave once obtained, and so I could reduce the number of samples for the sine wave from 64 to 32, basically over a factor of 2. I now needed only 5 digits to count all the samples, and since we are talking about reducing the number of samples by 2 times, I would think that we could push the frequency about twice as much than the case from the previous video. With this solution, to avoid the obvious digitization errors in the sine wave, I added to the schematic from last time just a single capacitor at the very output of the digital to analog converter. The second problem that needs to be addressed is the one of the glitches in the signals that I see on the oscilloscope. In the comments, it has been suggested that probably the 2 ISR functions, the one for the generation of the signal and the one for the reading of the frequency value, are interfering with each other and one will cause delays in the other. The proposed solution were to reduce the time the Arduino has to spend within an ISR function and make sure that while the Arduino is within an ISR, the other one is not called. Even better, if it is possible, is to establish a priority between the 2 ISR functions. Now, the Arduino is made in such a way that when we are inside an ISR function, the interrupts are disabled, and therefore any other interrupt will not cause another ISR to run. This is a sort of priority, but is the priority of the first come, first served. There is no way to establish different priorities for different interrupts in the Arduino. However, there are still a couple of things that I can try to mitigate the glitches in the generated signal. First, I can try to limit the number of times that an ISR is executed, so that we have less chances that it will interfere with the other one. Now, this is already done for the ISR that generates the signal, because with the first change I already have reduced the calling frequency by a factor of 2. For what concerns instead the length of the execution of the ISR functions, the one for the generation of the signal cannot be reduced any further, but I can still work on reducing the execution time of the ISR that reads the value of the potentiometer. And in fact, once I read the value of the potentiometer, rather than executing all the calculations inside the ISR, I can move them in the loop function, which can be interrupted any time without any problem. As a matter of fact, I can even remove entirely this ISR, since there is no need to sample at precise times the position of the potentiometer, and so I can move all that section within the loop function. This solution will also work on the other problem for interaction between the two ISR functions. Since now there is only one, the problem is solved automatically. There are only one, so there are no interactions. Let's take a look at how I implemented all these solutions one at a time, adding them one by one to the original software from the last episode. Here is the code for the first solution, which is all about using only a sine wave and reduce the number of samples from 64 to 32. And in fact, the wave table here has now been reduced to a single vector of 32 elements, addressable with 5 bits rather than the previous 6. This will reduce of 2 times the rate at which the samples are written on the output register D. The constant last sample has now a value of 31 instead of the previous 63. Remember that we start counting from 0, and so for 32 elements we go from 0 to 31. The setup function has not changed. We still need to set up 2 timers and corresponding interrupt service routines, or ISRs. Talking about the ISR functions, let's take a closer look at the one for timer 2. Since the number of samples per period has been reduced 2 times, now we need to load a different number in the OCR register, which is the one that is compared with the value of the internal counter to determine if an interrupt needs to be generated or not. Everything else is exactly the same. Here is the circuit from the last time, and here is the new capacitor that has been put at the output of the digital to analog converter. Everything else is basically the same as in the previous episode. So now let's connect the Arduino to the computer and let's upload the code. Here is the code that we already examined. And what I'm gonna do now is to just upload the code to the Arduino. So we click here, uploading, done uploading. So now we have everything in place. What I have left to do is to connect now the oscilloscope so we can see the wave coming out. Here, this is ground. Okay, and this is the output. And let's go to take a look at the oscilloscope now in this condition. Okay, seems like the frequency is very low right now, and which is right because the potentiometer is all the way to the left. So let me change the scale on the oscilloscope, also the amplitude, and here's the sine wave. And it is a 20 Hz wave. Perfect. So you can see there is some scaling over here, but and if I remove the capacitor, let me do that for a moment so you can see what the shape is without the capacitor. See, it's much more rough in this condition. So let me put back the capacitor and we can take a look again. So you see this is much smoother. Okay, so now I'm gonna change the frequency again as usually with the potentiometer and see where we can go with that. Right now the shape seems okay. Let me increase the frequency a little bit. Ooh. Just a little bit for now. Okay, so now we are at about 54 Hz. And it's still reasonable, but you see now we started having all the issues of the last time, so that they didn't disappear. Let's see if at least we have the possibility to increase the frequency enough this time. So now we are 580 Hz. If you remember last time we were able to go up to about 3 kHz. Let's see where we go now. Let me increase a little bit here. We can still see the wave with all the issues along with it. Okay, we already passed the point from the last time, and so it looks like there is already some kind of improvement. 6 kHz, look at that, 7 kHz. And now I keep rotating the potentiometer. Oh, look at that, 8.7 kHz, 8.9, 9 kHz, 9.9, 11 kHz, 12 kHz. So you see, just removing 1 bit from the resolution of the sine wave has helped us having much better frequency. So with the range of frequencies now we are okay. We just need to remove all these glitches all around. Let's see if we can do that with the next change. The second test uses basically the same code as the test 1. The only difference is on the frequency at which the voltage of the potentiometer is read. Since we had already used the bigger variable prescaler, I added a new variable to enable the actual reading every other time the ISR for timer 2 is called. I call the variable just scalar to remember that it has to do with the prescaling. The variable is initially set to 0. Later on, when the ISR is called, the value is incremented, and if greater or equal to 2, then it is reset to 0, and the reading of the potentiometer value is done, along with the calculations to determine the actual frequency. Then the content of OCR1A is updated. This way, when the ISR is called for the first time, scalar is incremented to 1 and nothing else happens. At the next call, scalar is incremented to 2, immediately reset to 0, and the rest of the procedure is done. At that point, the cycle goes back to the beginning. The result is that the actual procedure we need to run in the ISR is executed every other time the function is called, and therefore multiplying the execution time of the procedure by 2. It is like we were able to set the prescaler to 2048, even if that number is not available in the Arduino. Reducing the number of times this ISR is called per second should reduce the chance of interference between this ISR and the other one for timer 1. Let's see in lab if this provides any benefit. So let's upload the code to the Arduino. Uploading, done uploading. Okay, and the oscilloscope is still connected to the circuit, the same as before. Let's go to the oscilloscope over there. And, well, no, we still have the same kind of issues. You can see we still have the glitches. They didn't go away. Well, it behaves a little better, but not that better. So, we got some improvement here, but not that much. Let's see if the next change helps in reducing even further this kind of problems. Since reducing the number of calls to the ISR functions didn't provide any benefit on their interactions, let's try now to eliminate entirely the interactions by eliminating one of the two ISR functions. We do need the ISR for timer 1 because we need to make sure that the samples of the sine wave are provided at the exact moment. But we don't really need the ISR for timer 2, because even if the readings of the potentiometers do not happen exactly at constant intervals, we should not have any bad effect on the generation of the signal. Based on this thought, I entirely removed the ISR for timer 2 and put its code directly inside the loop function. In addition, I don't need to make any calculation and change the OCR1A value if the previous read is the same as the last read. And so, if these two values are the same, I just skip the calculations of the frequency and the update of OCR1A. Otherwise, I run the procedure, and I also update the now old value at the potentiometer. Then, before leaving the loop function, I increment the scalar value, and then I check for both the scalar to reach the number 10 and the value of the variable readpath to be 1. Why is that? Let's go back to the only ISR left in the program. You see, this new variable is set to 1 only at the end of each period of the sine wave, which is when we reach the last sample. At that point, in addition to reset the value of the sample number to 0, we also set the readpath to 1. Back in the loop function, the if at this line tells us that we do the analog read only if a period is completed, because of the new variable, and we have passed through this point of the loop 10 times, because of the scalar variable. This is basically a way to reduce the number of times we do the analog read, rather than doing it every time the loop function is executed. So, summarizing, this change removes entirely the necessary ISR for timer 2, and also executes the analog read only a limited amount of times, which is smaller than the frequency of the sine wave by a factor of 10. Let's see if this helps now.
And here are the last code changes. Now we have the extra variable spot value and old pot value that allow us to remove one of the timers. In fact, you can see on the setup function now we have only the timer 1. And now we have the loop function populated with what was the content of timer 2 ISR. So let's upload this and let's see if it makes any change again. Let's go look at the oscilloscope, and we are still there. The problems are basically only about, we are going to about 12.13 kilohertz actually. See, we are hitting 13 kilohertz, but it's not constant, which means that the ISR function for timer 1 is not called exactly at the moments where it's supposed to be. There is some shifting in time, and therefore some phase shifting in the sine wave, which causes these things to be seen. So there is still something in there. Some other interrupt that probably is interfering with the timer 1, and we need to figure out what that is.
At the end of the game, it looks like there is still some sort of interaction between the only ISR function left in the program and some other interrupt routine hidden within the Arduino code. A little research demonstrated my theory. The analog read function attempts to periodically read the internal analog to digital converter until a value is available. That is because the ADC takes some time to do a conversion, and the timing for these attempts is given by an interrupt, and that is periodically invoked until the analog to digital converter of the Arduino is ready to provide a value. And so we still have two interrupts to deal with. If I didn't have to use the analog read function, probably all my problems would have gone away already. And as long as I use the potentiometer to read the value of the frequency that needs to be emitted, I will have to use the analog read. Even if I replaced it with some other code, I would still need a timer to periodically check the ADC readiness, or at least I would need an interrupt for a synchronous read of the ADC. So the interaction problem with this approach is here to stay. But here is the thing, I added the potentiometer to be able to quickly experiment with different frequencies. If I decided to use such a circuit with some other mean of defining the frequencies, for example by presenting the frequency value directly on some of the digital inputs, I could eliminate the problems of using analog read entirely. And that is exactly what I wanted to do from the beginning. The potentiometer is there just for experimentation. What I really wanted to do is to present to the Arduino a frequency value already digitally encoded, and the Arduino will only have to generate that frequency. So, all in all, these experiments provided some good data to use, and proved that yes, it is possible after all to generate complex waves with Arduino using a wavetable. At this point, I think I obtained what I needed, and now I am ready to go to the next step of the project I am working on. Yeah, no, I'm not going to tell you yet what the project is. I'll let you take a guess for now, and at the right time I will reveal the secret to all of you. In the meantime, keep following my videos, and to avoid missing any new issue, subscribe to the channel and click on the bell to enable the notifications. Thank you for watching this video, and as usual, happy experiments!